a group of researchers say they've identified at least 7 stars that might be surrounded by super advanced alien megastructures known as Dyson spheres.
What if someday we could build a superstructure so big we could basically surround our sun and capture its energy directly?
There's something called a Kardashev civilization, named for Nikolai Kardashev. He was an astrophysicist. If you look at the history of what we call great civilizations, one of the things that distinguishes them is their capacity to generate and consume energy.
So why would the smartest life in the galaxy choose to surround a star when thermodynamics guarantees every captured watt must be thrown back as heat? When you intercept starlight, you don't get to keep it. You convert it into work, running habitats, factories, computation, and then you must pay the bill and waste heat. That's not a quirk of engineering. It's the second law of thermodynamics. So, the more energy you harness, the more you must radiate away. If you wrapped a star in orbiting collectors and used that power at roughly room temperature, you'd re-emit most of it as mid-infrared light. In other words, cosmic paparazzi need only infrared cameras to catch you. We talk about power as a hallmark of advancement, but physics insists that every triumph has a glow. If waste heat is the unavoidable receipt you hand back to the universe, what, exactly, would star-wrapping civilizations look like through our instruments? What would star-wrapping civilizations look like through our instruments? Their host star might appear under luminous invisible light and show an anomalous infrared excess, a thermal spectrum peaking in the mid to far infrared, approximately blackbody-like at temperatures from a few hundred down to a few tens of kelvins, set by radiator temperature and coverage. But because interstellar dust can produce similar warm, near-blackbody emission, often with silicate or PAH features, the two can be hard to distinguish, especially in broadband surveys. Scale that up to a whole society. If a large fraction of stars in a galaxy were wrapped, the entire galaxy would redden in the infrared. We've actually looked for this. Space telescopes that survey the sky at these wavelengths have scanned millions of stars and thousands of galaxies, searching for anomalies that can't be explained by dust or star formation. So far, we've found very few credible candidates. That doesn't mean no one's out there. It means galaxies aren't ablaze with obvious megastructures. Add the engineering reality. To intercept most of a sun's light at Earth's orbit requires collector area roughly equal to the surface area of a sphere at that radius, and material on the order of small planets. Building that quickly, safely, and stably is hard, and it paints a bright thermal target. Given the cost and the spotlight, what would a wiser path to cosmic capability look like? What would a wiser path to cosmic capability look like? It might look like a civilization that values information per joule more than joules per second. Landauer's principle tells us that erasing a bit of information costs at least kTln2 energy, where T is temperature. So if you want to compute more for the same energy, you get cold. That favors large, thin radiators far from stars or computation that waits for a colder universe. The aestivation idea goes further. If you care about maximizing total computation, you hoard resources now and do most of your work when the cosmic background is much cooler, increasing the number of irreversible operations you can afford per joule. Even if you don't wait, you can design reversible logic that minimizes erasures, and you can distribute your collectors into sparse swarms that radiate at tens of kelvins, glowing at long wavelengths that are harder to pick out against natural backgrounds. When you do need energy density, black hole accretion can convert matter into usable energy far more efficiently than fusion, yet the waste heat still obeys the same rules. A power-wise but information-rich civilization would be diffuse, cold, and quiet. Hard to spot, not because it's weak, but because it's efficient. If that's the wiser path, how should we aim our own ambitions now? How should we aim our own ambitions now? By upgrading our metric of progress. Keep power in the ledger, but add 2 axes, entropy management and longevity. Ask not just how many watts, but how many coherent operations per joule, and for how many years can we sustain them without destabilizing our environment? That reframes what counts as a milestone. Space-based solar becomes more than a quest for terawatts. It becomes a laboratory in low-temperature radiators and waste heat routing. Data centers become thermodynamic engines, judged by bits per joule and their ability to recycle heat into useful gradients. Planetary stewardship stops being a moral add-on and becomes a prerequisite for any future where we scale beyond our world without burning our own nest. Even the dream of megastructures becomes conditional. Not a monument to energy hunger, but a tool deployed only if it increases information per entropy and extends the life of stars or civilizations that depend on them. So the absence of glaring infrared beacons may not be a sign of emptiness. It may be a sign of maturity, civilizations that chose to master physics rather than challenge it with brute force. If we're to join them, our task is clear. Learn to do more with less, stretch time instead of power, and measure success by the stability and depth of experience we sustain. Per unit of heat, we hand back to the cosmos. In a universe ruled by thermodynamics, the pinnacle of advancement is not to shine the brightest, but to run the longest, the smartest, and the coolest. Like if this was interesting and hit the subscribe for more.